right, back at it again. Business Calculus section 1.7, last section of the chapter. And this section is about exponential growth and decay, something that we've already talked about. I guess they ran out of titles. This section is really like loose ends for exponential functions and logarithmic functions, which we've talked about in the previous two videos. So if things were not making sense in those videos, or if there's something that you still didn't understand about exponential functions or logarithmic functions based on the previous two lectures and working on your homework, well, maybe it'll finally make sense now. And if those videos did make a lot of sense, well, then this will really solidify your understanding for exponential and logarithmic functions, which I'm having a lot of difficulty saying at the moment. I hope. Not that I hope that I'm having difficulty. I hope you'll understand it. Okay, so let's get started. Okay, the first thing that we're going to talk about is future value. Now, we don't really have a new concept, a completely new concept to teach you in this section. It's really building off the previous two sections. So keep that in mind when we define this concept of future value. I haven't defined it yet, but let's just review for a moment that there are two different ways to write the exponential formula. You can write it in terms of an annually increasing rate, R, and we don't actually write R in the formula for that version. We write the growth factor, which is 100% plus the rate that it's changing. We also have the compounded continuously version formula of the exponential formula. And whenever you see this word continuously, you know to use the e to the kt formula. Okay. So K and R are kind of similar. K turns out to be result in a little bit more of an increasing function than the one with the R, if the K and the R are the same number. All right, so let's see. For example, a bank account starting with $85 and an account bearing 7% interest compounded annually for 3 years. How much would that yield? I don't see the word continuously, I see the word annually. So I know to use this formula. So we have the initial amount, we have the growth factor, which is 1 plus the rate of 7%, and the length of time that the interest accumulated. And when I calculated that, I got $104.13. Let's contrast that with compounding the interest continuously. And when we compound it continuously, we think the letter E needs to be in our formula, Euler's number. And in that case, we have the initial amount times e to the kt. And make sure to remember your parentheses there. And when I did that, I got $104.86. Notice a couple things here. Notice that I don't have to the power of 1.07 times 3. No. It's just the rate as a percent. Here we put 1 plus the rate. So notice that little difference there in the way we write it. I hope you've probably already made sure you're not doing that, but just in case. All right, and the other thing to notice is that what's the difference between our answers here? It looks like we got a little bit more in this case, even though the rate was the same, right? But this was a continuous rate, meaning that a portion of the interest was added on each moment, right? And after it gets added on, it starts earning that interest that gets added on starts earning interest. So even though you're only adding on a tiny bit, it starts earning a tiny bit of interest. And so by the end, you end up with a little bit more than you would if the interest was added on all at one time at the end. So I recommend that you do this whenever you're working problems. Whenever you get answers, just think, okay, does that answer make sense? This is something that I know many of you are not used to doing, but it will be very helpful to you in your understanding of the material and digestion of the material if you think about, okay, I got an answer. Does that answer make sense? For example, if I started with $85 and I did some calculation and I ended up with like $70, would that make sense? And no, it wouldn't make sense because I'm investing some amount and it's earning some interest. So I would expect to get a number bigger than what I started with. That kind of thing. You just do it kind of a sanity check, what some people call a sanity check. Okay, enough about that. Now, finally, this slide was called future value. This amount that we ended up with, that's called the future value. All right, so we're thinking of it like some amount in the future that we would end up with if we started with $85 at some interest rate for some period of time. That's what future value is. It's the amount that you'll end up with later on, assuming that you invest a certain amount for a certain length of time. That's what future value is. All right. Now we will talk about present value. So we just found that if we invest $85 today for 3 years in an account bearing 7% interest compounded continuously, if we didn't die of exhaustion from running out of breath after saying that, then we'd have a future value. We'd end up with $104.86. Now, present value, it's the opposite thing, right? So instead of the amount that you'd end up with, if you started with some amount, it's the amount that you'd need to start with if you had a number in mind that you need to end up with. All right, so in this case, for present value, that would be the amount that we'd need to invest if we desired to end up with a certain amount later on. Okay, so if I want to end up with $1,000 in 3 years, and I'm able to invest it at a 7% interest rate compounded continuously, then can I figure out how much I'd need to invest now? And yeah, I can. So let's do that. So first of all, I write my formula. I always do that. I like to do that. I know that I'm investing in an account that's bearing continuous interest rate, so I'm going to have an E, the E form of my formula. And I know the amount that I'd like to end up with, $1,000. And I know the interest rate, and I know the length of time that I'm going to invest it. So I've just entered in everything that I knew, and what I get is an equation with only one variable, and I can solve for that. So e to the 0.07 times 3, that's just a number, right? So I've got a number times p naught, and so I can just divide by that on both sides. And when I do that, oh my goodness, it's not aligned. All right, these equal signs are supposed to line up. Unfortunately, they aren't. Huge apologies for that. Anyways, when you do that, you get $810.58. Okay, so what we've just calculated, what we've determined, is that if I want to end up with $1,000 in an account that bears 7% interest for 3 years, then I'd need to invest $810.58. That's what I figured out. All right. So that's that. Let's move on. Doubling time. Okay. So let's talk about doubling time now. This would be the time that it takes for the account balance to double, or some initial value to double. So for maybe that's a population. Our examples are usually have to do with balances in an account. All right, we're not very creative, so we just think about money. All right, so how long would it take for $85 to double? That means that we end up with $170. And what's given to us is that our account is going to increase at a rate of 7%, and that's compounded annually. I do not see the word continuously, so I know that I need to use the form a to the t, the formula that has a to the t in it, right? Not e to the kt. Okay, so so I'll write that down, and I didn't have enough space to write it initially. Ended up making 2 slides out of this, so I probably could have fit it on there. But anyways, all right, so we end up with $170. We started with $85. And what goes here is the growth factor, A, which remember is 1 plus the rate of 7%, so I get 1.07. All right, now, just to make sure you don't do this, I'm going to point out where I've seen students go wrong in the past. From this stage, they immediately took log of both sides, and you don't want to do that. You don't want to do that. It's not wrong, but you probably won't get it right by the end. You'll probably mess something up. It makes it harder. So at this stage, the thing that you should do first is divide by 85 on both sides. So you got 170 divided by 85, that's 2. And on the right-hand side, you're left with 107 to the power of t. All right, now you want to take log of both sides. You want to solve for this exponent that is a variable. And that's the whole point of logarithms, to solve for equations where the exponent is the variable. All right, so we take log of both sides, ln. We never take log of some specific base. That's not e. We always just take ln of both sides, because that's all we need to do. So we take ln of both sides. The whole point is that allows us to bring our exponent, that's the variable, out in front. And then I can divide by ln of 1.07. And I get that t is ln of 2 divided by ln of 1.07. So at this stage, I'm going to enter this in my calculator and come up with a number. And when I do that, I should get 10.25. And I put years here. How do I know that it's years? T was in years. T was in years. Okay. So 10 point, and I think I wanted to say something about this. I'm not sure if I want to say it now or later. Let me just say it now, and you can keep it in mind for later. So whenever you're solving an equation, it's a good idea to do all the algebra first without rounding anything, and save your rounding until the very end. All right? Notice that when I took ln of both sides, at this point, I could plug in ln of 1.07 to the calculator and come up with a number, and then divide by that, right? And then I'd round again. But the problem is that when you round in the intermediate stages, you might round off, you don't actually know how many decimal places are important in the intermediate rounding calculations. So I recommend that you do all the algebra, and then you get an answer, you solve for what you wanted to solve for, and then you put that in the calculator in one step, and then you round once. Okay, just keep that in mind. It wasn't so important in this particular problem, but it does come up, especially for business calculus, keeping track of lots of crazy numbers. Yeah, it's just a good rule to remember. So anyways, this was doubling time, which is the amount that it takes some amount to double. Now, did it actually matter that we started with $85 and ended up with $170? And the answer is no, it didn't. It didn't. Because no matter what I started with, I would end up with double that amount. And so after I divide by that initial amount, I will always end up with the equation 2 equals the growth factor to the power of t. All right. So assuming that I'm talking about the same interest rate, it didn't actually matter that I started with $85. So the problem really starts at this line. if that didn't make sense, then you can start here, and it's not a problem at all. You won't get it wrong, but it actually didn't matter how much we started with. If we started with $100 and wanted to know how long it took to grow to $200, or if we started with $900 and we grew to $1,800, we would get the same answer, 10.25 4 years. And that is because exponential functions grow at a constant percent rate of change. So after 1 year, it always grows by the same amount. And another way we could say that is it always grows by the same amount, the amount of time it takes to grow a certain percent is the same. All right, I didn't maybe say that the best, but hopefully you got some of that, some percentage of that. All right, let's move on. So that was for compounded annually. Let's see how the situation would be different for continuously compounded interest. Well, if we're going to compound the interest continuously, then we need to use the version of the exponential formula where the interest is compounded continuously. So we're going to have an E, and I'll just put in my numbers. Final amount, starting amount, $85. Interest rate is 7%. I won't put 1.07. No. Okay, divide by 85. I, again, end up with just 2 equals this. The problem really starts here. Now we want to solve for this. Now we're ready to take ln of both sides. So I've done that here. And that allows this entire exponent, 0.07 times t, out in front. And I didn't write ln of e. Why didn't I write ln of e? Because ln of e is 1. And 1 times a number is just that number. So this simplifies just to the exponent. All right. And then I want to solve for t, so can I just divide by 0.07 on both sides? Yeah, I can do that. All right. So I get the answer is ln of 2 divided by 0.07. And when I entered that in the calculator, I got 9.90 years. So it took less than 10 years to double if the interest is compounded continuously, and it took more than 10 years to double if the interest was compounded annually. And does that make sense? And the answer is yes, it makes sense, because if it's growing continuously, then it's growing faster, right? Some portion is being added on at each moment. That portion starts earning interest itself, so the function is actually increasing a little bit faster, so it takes less time to double because it's increasing faster. Okay? You should always try to make sense of your answers. Do some sort of check. Whenever you get 2 answers, compare them. See if, does it make, I got this number was greater than this number. Does that make sense that I got that? If the answer is raising some alarm bells, then that's an indication that maybe you made some mistake in an earlier calculation. And we use that a lot in math. We look at the answer that we got and we see, is that kind of in the ballpark of what we expected? If the answer is no, then we need to look back at what we did, and often that will help us find a mistake that we made, which happens a lot in my case. Okay, that is that. Now we are ready to talk about half-life. Half-life is very similar to doubling time. We're finding a length of time that it takes for a function to decrease by 1/2. So we're not talking about decreasing by some amount. We're talking about it decreasing by a percentage. So, for example, let's say we take some Tylenol, which has a continuous decay rate of about 24% per hour. So each hour, only about 76% remains of the amount that you started with. Okay. And suppose we want to know how long it will take to end up with half the amount that we started with. All right. Let's see. Our formula, is this the right formula? P of t equals p naught times e to the kt. And the answer is yes, that is the right formula, because it has a continuous decay rate, so I need to use the E formula. I have written here k equals negative 0.24. Is that the right k? I have a negative. Why is it negative? Because the function is decaying, is decreasing. And whenever I write 24% as a decimal, it's 0.24. All right. Now, in this case, we don't know the length of time. That's what we're trying to figure out. We don't know how much you end up with, and we don't know how much we started with. It doesn't say any of that in the problem. But let's see if we can solve it anyways. Now, we do know that we end up with half the amount that we started with. So I do know that the ending amount divided by the starting amount is 1/2. Right? That's what it means for that ratio to be 50%. It equals 1/2. All right. So I will just I will just pretend that I have divided by p naught on both sides of this equation. I end up with 1/2 equals e to the kt. At this stage, I'm ready to take ln of both sides. And so I do that. That allows my exponent to come out in front of the logarithm. It does not come down beside the logarithm out on the right hand side. No, it comes out to the left. And then we have ln of e here. What's ln of e? That's 1, because e to the first power is e. And so 1 times anything is that anything. So we just have, this is just this. The ln of e doesn't need to be written here. And so I have a number times t. Haven't changed the left-hand side. So I can solve for t by just dividing by negative 0.24. So I'll do that there. I'll make sure to remember my parentheses where they're needed. And then I'll just do that calculation. And when I did that, I got 2.89. And I said hours because t was defined in hours, defined as a rate. That rate is given as a percent per hour. Okay. Now, we got an answer. What I'm trying to train you to do is, after you get an answer, to not blindly enter that in, but to actually take a moment and think about, does that actually make sense as an answer? All right? Because if it doesn't make sense, then that means that will actually help us figure out what we're not understanding. There's something that we don't understand. All right? All right, so let's think about this for just a second. We got that this was about 3 hours to end up with half the amount that we started with. Now, when we look at this, it says that it's decreasing by 24% per hour. Now, you might expect that it would only take about 2 hours to end up with half the amount that you started with, because after 2 hours, 2 times 24% is about 50%. So that would decrease by 50%. But that's not the exact right way to think about it. So there's an issue with the way thinking about it like that. This is decreasing by 24% per hour of the amount at the beginning of each hour. So after it has decreased, you're starting with less at the beginning of the new hour, so 24% of that will be less. So it's decreasing by less and less. So for that, so what we're talking about, ending up with half the amount, that's ending up with half the amount of the beginning of the first hour. Okay, so it's going, so after the, for the second hour, it's going to decrease by a number that's smaller than 24% of the starting amount at the beginning of the first hour. All right, so it's not, so we can't count it as 24% like that. So it does make sense that it took more than 2 hours and about 3 hours. That does sound reasonable. All right, but yeah, that's that. It's a good thing to think about though, because when we get an answer that we don't expect, that really helps us figure out what we didn't even realize that we didn't know, that wasn't even on our radar before. It just points it out to us. There's something that I'm not understanding. Either there's something wrong with my calculation, or I don't understand exponential functions, something about exponential functions. It doesn't mean you don't understand anything. It just means that there's something that you're not understanding. And it's always good to know that. All right, so that is that. Ready to move on to our last example for the day, or the video at least. So in this example, I tried to come up with an example where you know everything except the rate. All right, we haven't actually seen an example like that where we know everything except the continuous decay rate or continuous growth rate. All right, we know, but in this example we know everything but that, and let's see if we can figure it out. So here's the example. Suppose we start with $250, and after 15 years we had $450. Could we figure out the interest rate that it increases, assuming we didn't touch the balance? You know, it just stood in the account in accumulated interest at a continuous rate. Could we figure that out? And the answer is yes, we can figure that out. So let's do that. So I know I'm going to use this version of the exponential formula, the one with the e, because, well, it's compounded continuously. And I know the initial amount in my account is $250. And I know the amount after 15 years is $450. So I know what the formula looks like, and I know some things, so I just plug them in and I see what I get. And we do this a lot in math. So we just kind of have to put one foot in front of the other. And after I plug everything in, I get an equation that only has one variable, and I think that I can solve for that. So let's see. First, I should divide by this 250. What should I not do? I should not take logarithm of both sides at this point. I should first divide by 250 rather, and I get this. I will write k times 15 as 15k. Looks a little nicer. Now I'm ready to take logarithms, so I will do that. I'll take log of both sides. The whole point is that that allows my exponent to come out in front. The ln of e disappears because that is 1, and 1 times anything is the anything, which in this case is 15k. And then I will divide by 15 on both sides, and I get this, and that is k. And I have not done any rounding. I have not done any calculator work until this point. I did everything. I did all the algebra, and now in one step I will enter this into my calculator, and what I will get is 0.0391. Right? I will not take my calculator. I will not go 450 divided by 250. What is that? Okay, what is ln of that? Okay, let's divide that by 15. I won't do that. I will just enter this in one step. And then if I get it wrong, or I did something wrong, you can actually hit second enter on your TI-83, 84 calculators, and it will bring up what you wrote, and you can go in and change something, change one small thing. Maybe you forgot to put a negative sign or something, or parentheses. You can add that in. But calculator, just do everything in one step, and then look at it afterwards and make sure it's right. Anyways, what we get is, man, I am really preachy today. What is wrong with me? Okay. But anyways, I get k equals 0.0391, and when I write that as a decimal, I get 3.91%. So apparently I did it. We did it. 3.91%. That's the rate at which it increased per year. Now the amount that it increased each year was going up because we had an initial balance at the end of each year that was higher than what it was before. So the percentage of that amount was higher than it was before, and so it increases by more and more, and that's how we get that concave up shape for exponential growth. All right, well, that will about wrap it up for section 1.7. Good luck, as always, on your Wiley Plus homework. And if something doesn't make sense, of course, you can email me or come to office hours or research the problem online yourself. Maybe you could find a YouTube video of someone that explains it even better than I can, although I doubt it. But you can always try. All right, with that, have a good day. Goodbye.